Hi, everybody. This talk is going to be in English. You can see me here diving in our data lake. As you can see, we have lots of data. So this talk is going to be about anomaly detection at scale. Looking at the agenda for the conference, I realized there were 3 talks about anomaly detection. And I think this constitutes an anomaly. And yet, I think they're all complementary. There was a talk about the data itself and distributions. There was a talk about avoiding false positives. And in this talk, we're going to focus about scale. I want to start off with the problem with data. If you look at this image, you can see Waldo. If I ask you where Waldo is, it's obviously very easy to find him. He's right there. But if I ask you where Waldo is now, that's not so simple. And the more people we have here, the more difficult this becomes. So this is not a property of Waldo. This is a property of the amount of people around Waldo. And the same thing happens with data. The more data you have, the harder it is to do certain things. And we'll talk about them in this talk. So one of the problems with data is scale. If you look at why scale is such a big problem, take a look at this. If you know how to ascend a small hill and you want to transition to ascending a mountain, you immediately can see that it's a totally different problem. First, the mountain is much steeper. And second, there's new features in it. You can see the snow and ice on top, right? So to ascend this mountain, it requires special equipment, special training. It's a whole different ballpark. If we look at a small-scale country road, just a simple road, you can see it's a simple road that handles traffic well, just 2 lanes and a divider line. If we have more and more traffic and we want to scale it up, the common sense approach would be to maybe duplicate this road. But this will not really work. And the reason is because of bottlenecks that will start creeping up on us. In the case of roads, the bottlenecks are intersections. As intersections grow and grow, this becomes more and more difficult. They become a bottleneck. So to design a large road that can handle a lot of traffic, we have to take a different tactic, a different approach to it. And in order to be able to handle all this traffic, we need to add new features to the road. And the new features are aimed at solving all these bottlenecks that crop up. If we look at a road, the new features we add, just to name a few, are interchanges, right? On-off ramps, which allows the cars to speed up so they don't slow the traffic on the road. Suddenly, the road becomes complex. We have to add direction signs. People get lost on the roads. Cement dividers, traffic light at feeder roads, and so on and so on. Every one of these features is aimed towards solving some particular bottleneck of scale. And only if we do all of them well, we can ascend to the next level. So our data at Nielsen, and I'll say a few words about Nielsen soon, we have a lot of data. And within that data lurk anomalies. In total, we have over 1.1 million time series that we'd like to detect anomalies in. And in this talk, we'll talk about these anomalies. I'll tell you about our little anomaly project, how we detect anomalies. We'll go into the scaling problems that I mentioned and see where they apply within the data and the system that runs it. And you'll see the secret sauce we use to solve these problems. And hopefully you can take some of these ideas into your projects as well. Before we go on, I want to introduce myself. I'm Director of Data Engineering at Nielsen Marketing Cloud. We're actually located right here in Sarona, Israeli Sarona. I am a big believer in serverless. I think this is the next revolution after cloud. And you'll see that we also use serverless to solve some of the issues we ran into. A bit about us, so you have some context. We're Nielsen Marketing Cloud. We build marketing audiences and device graphs. And this is great for running marketing campaigns and for making business decisions from the data analytics you gain from it. An audience is basically just a list of IDs with some classification, a trait. A list of IDs are device IDs, which we basically equate to users, right? So there could be a group or an audience of pizza lovers and people who are into running and cycling enthusiasts and so forth. And this is really useful. You can have a lot. The list, by the way, could be different sizes. This is really useful. Marketers love this because they like to intersect these groups and then run marketing campaigns towards these devices or users. So think about it. If there's some cycling event going on in this area and I'm a pizza chain, I might want to run a campaign during that time for people who are cycling enthusiasts and love pizza and maybe send them a coupon to our pizzerias. So that's very useful data. Overall, we process about 60 terabytes of new data every day and classify it and store a total of 5 petabytes of data. We're heavy users of Spark and serverless Lambda functions. All right, so let's dive into our Anomaly project. And to explain it, I want to go into a further, explain what time series, which I mentioned before, is. So I mentioned the pizza audience, which might be 24 million people, but this data really accrues daily. Every day we classify more people, new people, with the label pizza lovers. So the data comes in like a time series, basically of volume of users that we classified that day. So we accrue points in time, and each one of these audiences is a time series. You'll notice one of the dots on the bottom here that I would bet is an anomaly. It looks really odd. Something has happened during that day. If I overlay a graph on it, it's even more obvious. You can see why I thought it's an anomaly. Our users and business users actually might be tracking lots of audiences. In total, we have in the system close to around 500,000 audiences, and it's practically impossible to track all of them manually. And think about it, if I'm running campaign and I'm depending on all these new users being classified, fresh users, and suddenly the volume drops, this is an issue, right? If I learn about it a few days later, that's it. The campaign is already gone. I can't recover it. I lost all these cycling enthusiasts that came for the event. So we really want to know about this before the end users discover it and maybe take corrective action. So in 2019, we were asked to create some system to alert on these anomalies. We started a pilot, went into beta, then we did some scale improvements, then we did some more scale improvements and a whole redesign. And the reason we had to do all of these is because data basically grew over time. We started out with 15,000 time series, and over time it grew until today it's about 1.1 million time series. And in total, we have about 150 million data points within the system. All right, so let's talk a little bit about predictions, and you'll see we had to go into predictions to detect anomalies. And I want to mention that Niels Bohr, the father of quantum computing, once said that prediction is very difficult, especially about the future. If you go back to the 1950s, people predicted that by now we'd all be driving flying cars or flying them around. And yet, when I drove here this morning, I did not see one flying car driving on the road, nor did I see one in the sky, right? So this prediction was totally off, and there were lots of predictions that were totally off. The reason is that the further into the future you predict, the harder it is to do, the more noise you have in your system. Gali from Tabula discussed noise in her talk. So this becomes difficult. If you look at a graph of how this actually looks, you see that the errors grow over time as you predict further into the future. But the flip side to this is that if you make short predictions, you have less noise and it's actually easier to predict. And for anomaly detection, we can actually take advantage of this to predict use our data for predicting and for finding anomalies. All right, so let's look at an example of weather, for example. Let's say I'm tasked with predicting the weather at noon. What I can do, I can look at the weather in the last hours, and I can see that it was really sunny and warm, just a nice day. And what I would probably predict for the weather in the next hour is that, again, it's going to probably be sunny and warm. We'll wait for noon and check the weather out. And if it's sunny and warm, we'll say, great, our prediction matched reality, our model works. We can do this again and again. But what happens if at one of the hours, 2 o'clock, for example, suddenly clouds come rolling in, the temperature drops significantly, and it starts to snow? Obviously, you would say, this is really weird, right? And you would declare this as an anomaly. Even more so, if I was registered to your alerting service, you would immediately send me an alert that something odd has happened with the weather. This is exactly what we do to detect anomalies, and I think some of the other talks talked about it as well. We basically make some prediction using some model, and there's lots of different models you can use, and then we compare it to the actual values. If they're off by a lot, we declare it as an anomaly. If you look at it from an algorithmic flow of just numbers, of these time series numbers coming in, we can basically use the data we have as a training set for the algorithm. We'll predict the next time period, wait for the data to come in, see that it looks okay, do this again. We could use the next data point as part of our training if we want, if we have a model that trains really fast, like some of the regression models. And then we could do this again and again. And if we get to some point where suddenly we have a data point that's totally off, like in this case, that it's 2.2 standard deviations, we would declare this as an anomaly and send an alert. All right, that's great. If we look at a graph of how it looks over time, we can see the data here. This is the prediction. You see the prediction is off from the actual data. Again, this is an anomaly. All right, so we have then to choose a model, but life is full of difficult decisions, so this is usually not really easy to do. You heard, if you went to the other talks, you heard a lot of talk about different models and trying different models for different things and optimizing them. We currently use the stats model library, and we use for exponential smoothing and ARIMA. And we wanted to design our system to be able to support future libraries. So we basically implemented an abstract class where all you have to do is to introduce new models is just implement the train and predict methods, and then you can include new models into your system. This is great because from the time we started with just predicting anomalies on audiences, we were asked to add more and more data sets. So we added more data sets about page views and all kinds of AWS instance metrics and so forth. And sometimes you need a different model for them. All right, so we understand what we are trying to achieve with our anomaly detection system. Let's dive into scale. Let's talk about the bottlenecks we had to solve. So the bottlenecks were the following. One, just getting it to run well with this amount of data was a challenge. We had to get the system really working well. There were challenges on the compute and on the storage side. Once we got it to run, we had to get costs down, because what happens with scale, as scale goes up, if your system doesn't scale behavior well and scales linearly, then your costs will escalate, and then that would pretty much kill your project. And the third thing is trust, which is a bit surprising, because I don't think you would, from the get-go, think that trust would be an issue with scale, but we'll see why it is. So we started out with our naive pilot with a relational database. We knew it's not going to scale well, but this was great for experimenting, running a pilot, quickly making changes. So this was awesome. We had a nice run with it. It was great for a pilot, was okay for a beta, but started becoming a bottleneck at scale. The classical way to solve scale of how people used to do that is if you had a problem with your database, you just get a bigger database. If you had a problem with compute, you get more servers or larger instances and just throw more power with it. The problem with this is usually there's bottlenecks that creep up from all kinds of dependencies, and as a result, your costs usually do not scale well, and which means as you double your data, your cost may go up by a factor of 3. And this obviously will blow up in your face as the costs accumulate and you start having bottlenecks and scaling issues. So our solution was to go out all out on serverless. We decided to use serverless compute units on AWS Lambda functions. We decided to use lazy execution. We don't want to pay for calculating anomalies if nobody's looking at them. We just want to calculate them just before people really need them. And if they don't need them for a whole day, we're not going to calculate anything. We're going to do everything last moment. And we decided to transition everything to low-cost storage, which means storing data, in our case, on AWS S3. We ended up with a system that has low cost and endless scale. I want to say a few words about serverless. So serverless, the idea behind serverless is instead of spinning up machines, instances, we have some unit of work. We can ask the serverless infrastructure to spin up some compute for us. It'll do the work and then terminate. You have to design your system for that. It means that the units have to be independent and they have to basically terminate when you finish your work. Otherwise, you're going to keep paying for it. But if you do that, then you only pay for processing, which is great. The resources spin up, do the work, spin down, and you can see that in all these idle periods in between, nothing is working. We're not paying for anything, which is really, really great. So we get unlimited scale and cost efficiency from this. Let's see how we implemented the architecture to do this with our anomaly detection system. So first, we have a Lambda work manager that wakes up periodically, checks what needs to get processed. Remember, we want to do this lazily, and creates messages on a queue that tells the workers what to do. The queue is a AWS SQS, simple queue service that we use, and it invokes the Lambda workers every time there's a message. The workers calculate new data if there's some pre-processing on the data. They run the models and the predictions and calculate anomalies and save the data back. If you look at a work unit, so basically one of these Lambda workers picks up a message. The message has a list of time series it needs to work on. It has the paths to where the data resides on S3. It reads some config that tells it what to do, maybe to aggregate the data over some period of time and which model to run. Reads the files from S3 with the old data, adds the new data, runs the predictions, save the results back, and only if it has anomalies would store them in a PostgreSDB. So we still use Postgres, but now it's an order of magnitude less data. It's just a small amount of data, so that is no longer a bottleneck. And this is great because we can calculate metrics and send the alerts from there and do analysis on it. So what did we get? We got low-cost storage, S3, we got low-cost processing, and we got endless scale. Let's see how low-cost it is. So for 10,000 time series that we run for a whole month, we pay a mere $2.70 for processing. Storage is negligible. It's a fraction of a cent. I don't even know how to say that. And the DB is another $1.66 per these 10,000. So for a total of $4.36, which is pretty much a cup of coffee, we can calculate 10,000 time series for a whole month every day. And if you remember, I said we had 1.1 million time series, so we pay less than $500 for the system for the whole month. So this is really negligible. And what it really means is that we can scale up from a cost perspective as well as scaling the system to any size we need to, right? There's no dependencies. Everything is independent. The costs scale up linearly. This is really, really nice. Okay, let's talk about trust. So a relationship will not really work if there's no trust in it. To make it work, you need to build trust. The same thing applies to a system. If you don't trust a system, you will stop using it. And I think Gali mentioned it in the talk about the Tabula alert system as well. So what is really trust? If you guys remember our prediction model, so if we had to predict basically the weather, we have some expectations of what the weather would be. So in this case, the model is predicting what's going to happen. Our expectation, the model predicted that it's going to be sunny. So we expect, if we trust the model, that it's going to be sunny. At noon, we look outside, it's sunny. We say, okay, this is good. So we trust the model a little bit more and a little bit more. And over time, if what we expect happens a lot, we start trusting the model or the whole system. Notice that this is really a step process. This is a journey. It's not a one-time shot. You make a small step, prove yourself, make another step, and so forth and so forth. And slowly, you gain user trust. You can also make some missteps and lose trust along the way. Let's take a look at how Tesla does it. So Tesla is building FSD, which is full self-driving. They expect this to be fully autonomous in a few years. Predictions about this vary. And what they're doing over time, they're introducing more and more features into the cars. Obviously, if you're driving a car and it has all kinds of self-driving features, you really need to trust it because it's really dangerous if it's wrong. And second, even if it's working well, but you don't trust it, you won't really use the system. So this is a view from a Tesla Model 3 in some intersection at Ramat HaSharon. What you can see is the windscreen on top. You can see we're at an intersection and there's a car there. And on the bottom, you can see the Tesla display screen with all kinds of info the car senses about the road. So you can see that there's two cars in front of us, one in front and one on the left. You can barely make it out. And there's a right turn that you can basically skip the stoplight and make a turn to the right. If you look at the car display, you can see that the car actually detected correctly the two cars in front of us, and it picked up the car coming on our right and making a right turn. If this was a video, you'd also see that it detects the car as it's driving next to us. More than that, you can see that it detected correctly the intersection we're at, and that intersection has 3 stoplights, so the car actually detected the 3 stoplights, and even the color of the stoplights, they're all red, right? So when I look at this, I'm like, nice, it's doing a good job. So how do I build trust? I do this over and over to reinforce it. It's a journey. So if we go and drive around and hit all kinds of intersections, and at every intersection, the car would correctly find all the important features, great. Over time, I'll start trusting this system. Notice that it didn't do it well in the last intersection, and that's okay. It's okay if it has some false positives or some errors, as long as they don't happen a lot. In our system, we did something similar. We realized if we give our users anomalies and we don't explain what they are, just with the sheer amount of data, they'll feel they don't have visibility into it, and maybe they won't trust the system. So we built a UI that shows you the actual data of the time series. You can select a time series on the left and see in blue the actual values that came into the system. And in the orange circles, you can see where the system detected anomalies. In green, you can see the predictions the model made, and you can see the differences. You can even figure out why it detected an anomaly where it detected that. What we discovered is people would look at this UI, scroll through some of the audiences, look at 5, 6, 7 audiences, and from that point on, say, if we'd ask, they'd say, oh, it's obvious, it looks fine. And they'll just stop looking at this because the trust was so high after 6 or 7 examples that they felt they no longer needed to do that. In the beginning, when we sent alerts, we just sent this data sentence with all kinds of metrics. And again, we realized that this is not trust building, and over time, people start questioning the system. So we've added a graph to the Slack messages we send as well to help with that. All right, so what would happen if we start having false alarms, right? So let's say I say this is an anomaly and send an alert to my users. If I do this a lot, they'll start losing trust in the system. And over time, this trust will degrade. And maybe it will degrade so much that it will go below some imaginary line there, right? So to prevent this, what we had to do is basically very finely pick the models so we don't get a lot of false positives. In our case, we wanted models that are very edge sensitive to the data, to the last data coming in. And we tweak the sensitivity so we don't alert on a lot of extreme data cases. If we did not do this, we might have been correct mathematically and detected anomalies that we would have considered correct, but our business users might have not cared, and this would have bothered them, and they would have stopped using the system. So creating many false alarms could degrade trust. If it drops below some imaginary line, people lose trust and stop using the system. All right, let's see what we talked about. We talked about designing for scale. We talked about keeping costs low. And we talked about building trust-enhancing features into your anomaly detection system and practically into any big data system. The recipe that we use for scale is using low-cost serverless parts that we could duplicate over and over and architected our system to be able to work in such a way. We used low-cost parts and ended up with the very low cost of the system, which allows us basically to process any amount of data we wanted. And for trust, beyond picking the right models so we get good data, we added visualization of how the system determines what it does, and we tuned the system for low false positives by making sure it's not too sensitive, even at the cost of missing out on some anomalies. All right, with that, I'm going to thank you, and thank you very much.